All right, so I got two questions about exam 2, so I want to go over them. One question was, when will internal energy equal enthalpy? And it gave you a series of options. I'm not even going to go through those options, but I will do, what I will do is kind of point this out. So enthalpy is equal to the internal energy, so this one is enthalpy, right? This is internal energy. And this is pressure times the change in volume. So when we're talking about gases, essentially the enthalpy is equal to the internal energy, the energy that went into it, plus this work, we call this pressure volume work, done by the system. So we talked about this in classes, like if you have like a piston, and let's say you have some kind of gas in here reacting, what it's going to do, if this is a piston, it's going to push this piston out. So if you have a gas that's maybe expanding, so let's say you have like 1 mole of a gas A plus, let's make this A2 plus B2, and let's say somehow it's yielding 2A plus 2B, so something crazy like this. So in other words, here we had 2 moles of gas because both of these had a coefficient of 1, and over here we now have 4 moles of gas. So what would happen is, to go from 2 to 4, if this were in an open system, the gases would expand, it would push this up, and I think we drew like a bunny or something like that on here, it would push this thing up, and so it would do work. All right, so that was a lot of explanation to say that when we're looking at pressure volume work, we're looking at the work done when a gas expands. So, so now let's answer the question, when will internal energy equal enthalpy? Well, that's going to be when things don't expand, right? In other words, internal energy will equal enthalpy when, and only when, this thing is 0. So when there's no change in volume. So you can look at all of those answer choices, A, B, C, D, etc. Then we get to E. All of these had a gas expanding or gas contracting. So there's always going to be a change in volume. But when you got to answer choice E, it said ... All this was reacting in a closed 40-liter vessel. And so what that means is that in this system, there could have been absolutely no volume change, and therefore enthalpy and internal energy had to equal each other. The next question I got was more of a stoichiometry type question. I didn't calculate this one either, but I will set it up. So we have 2 aluminum plus iron oxide yielding 2 iron and aluminum oxide. And then it says, hey, when this reaction occurs, it lets off 850 kilojoules of heat. So now it says, what mass of iron is formed when 572 kilojoules of heat is let out or released? Well, let's take a second before we even get to the question to see what this reaction is telling us. What it's saying is that when you react 2 aluminum and 1 mole of iron oxide, you're going to get 2 moles of iron, 1 mole of aluminum oxide, and it's going to release 850 kilojoules of heat. So the question isn't saying, hey, is saying, hey, if you know that this is going to release 850 kilojoules of heat and make 2 mole of iron, whenever you make 2 mole of iron, it's going to release 850 kilojoules of heat. What's going to happen if you release less than that? Well, you should expect it to be less than 2 moles of iron would be made. And we just use simple stoichiometry here to figure it out. We say, okay, we know that we've got 572 kilojoules of heat. We know that 850 kilojoules is released whenever we make 2 mole of iron. And this is how you would start by setting up the problem. But the question asked for the mass and grams of iron. So then you would say, okay, you know, a mole of iron has 55.85 grams, I think. I think it's 0.845. And then you can calculate it from there. But the most important step is start with what you got and use this as stoichiometry. For every 850 kilojoules of heat that was released, that tells you that you had to have produced 2 mole of iron. And when you calculate this answer, you should get the right one. All right, have a great week.